Analyzing an infrared spectrum. Focus on the diagnostic region. That's the region above 1500 wave numbers. It's even useful to take a ruler and draw a vertical line at 1500 wave numbers and focus on the stuff to the left of it. So these are the regions you want to focus on in the diagnostic. Signals between 1600 to 1850 wave numbers, you're checking for double bonds. Look out for carbonyls in this region. A carbonyl will tend to be the strongest signal in an IR spectrum if it's present. Looking at the region 2100 to 2300 wave numbers, check for triple bonds. These will always be lower intensity than a carbonyl. In the region that's 2700 wave numbers to 4000 wave numbers, check for bonds to hydrogen. These are at high wave number again because of the small reduced mass. Here it's helpful to draw a line at 3000 wave numbers. We'll come back to how to use this vertical line. And then of course you analyze the wave number, the intensity, and the shape for each signal. Right, you can differentiate between a pair of double bonds by saying, like, a conjugated ketone or a conjugated ester will have a lower wave number than one that's not conjugated. Broad signals are participating in hydrogen bonding. The more intense signals are between atoms that are further apart on the periodic table. That is, they have a greater difference in electronegativity, or the molecule is less symmetric. So when you're looking at the bonds to hydrogen, draw another vertical line at 3000 wave numbers. Signals to the right of that line are sp3 CH stretches. A sharp signal at about 3100 is an sp2 CH stretch. A sharp signal at about 3200 is an sp-CH stretch. You'll see amines at about 3400. These will be broader than the CH stretches, which will be very sharp. And you'll see a single stretch for a secondary amine, and you'll see two stretches for the symmetric and asymmetric stretch of a primary amine. If you're in an unsolvated environment, the OH stretch will be at about 3500 wave numbers, but if the concentration is high and or the solvent is capable of hydrogen bonding, the OH bond will be centered more at about 3000 and it'll be very broad and very intense. Again, the CH bonds will be sharp. At 3200 for an sp-CH stretch and 3100 for an sp2-CH stretch. The amine signals will be slightly broadened, but low intensity. The hydroxyl will be higher intensity and very broad if the concentration is high. Here's an exercise. Predict the important signals that we should see for this molecule in the diagnostic region of the IR spectrum. There are 4 important signals. So, predict their wave number, their shape, and their intensity. Pause your video while you work. Here's my answer, and we'll be starting at 1500 wave numbers and moving to the left at higher energy. That C double bond O is a carbonyl. This one will be maybe our most intense signal. It'll be around 1650 wave numbers. And it looks like a sword. The CC double bond will be medium intensity, and it'll be sharper, and probably around 1600. Now, we shouldn't see anything major until we get close to 3000. There are lots of sp3 hybridized CH stretches in the molecule. Oops, not there. I hate drawing hydrogens. But this will all add up to look like an intense feature, just less than 3000 wave numbers. But the really interesting CH bonds are here and here, the sp2CH stretch. That should show up sharp, medium intensity at 3100 wave numbers. Finally, we'll have an OH stretch. That should be intense and broad and probably around 3300 wave numbers. Unless the concentration is very low, in which case it'll be sharp at about 3400 to 3500 wave numbers. Here's a spectrum of a compound that has all of those same features. What we're seeing here is the CC double bond stretch. This is our carbonyl. This little tiny peak right here is our sp2CH stretch. These are sp3CHs. What we're seeing over here is the alcohol. The broad one is OH is involved in hydrogen bonds, and the narrow one is just plain OH.